Magandang araw. I am Jomar Fajardo Rabahante from the University of the Philippines, Los Baños. Today, I am going to introduce you to the exciting field of mathematical biology. In mathematical biology, we study biological systems using quantitative methods. We model complex systems as an alternative and easier route in finding solution to biological problems. To give you an analogy, when we were still kids, we imagined out-of-this-world dreams or ideas, such as huge living robots. But for us to make this tangible, we either paint the robot or create a robot out of materials that can be found in our homes. Then we can play with this creation, providing life to a modeled robot. Mathematical modeling is similar to this. Ideas and situations that seem to be intangible can be tangible by converting them to mathematical expressions. We can manipulate these mathematical expressions to find patterns. Patterns that can be useful in investigating biological systems. This is an example of a biological system. Here, a gene regulatory network that is translated to a mathematical expression, which is a system of differential equations, to come up with scenario results. I am now going to present a simple model. Let us try to model the population growth of a bacterial community. For now, let us use the concept of interest. Say you have a capital P of 0 and your money at time t is P of t after having an annual compound interest rate R. So at year 1, we have P of 1 equals to your capital plus interest rate times your capital. Then using factoring, we have this amount of money, the capital multiplied by 1 plus the interest rate. For year 2, we do the same, and the result is this expression. Now, let us assume that instead of annual compounding, we have compounding every 6 months or half a year. At the first 6 months, we have this. Then in year 1, the following is the expression. The general form for this case is P of t equals to the capital times 1 plus r over 2 raised to 2t. If we do daily compounding, we have P of t equals to capital times 1 plus r over 365 raised to 365 times t. Now, what if we want the compounding to be continuous? Then, we have this limit. From our calculus class, we know that this limit is equal to e raised to rt. So, we have the formula P of t equals to capital times e to the rt. Is this familiar? Yes, this is the exponential growth. And this exponential growth can be used not just for continuous compounding, but also in population biology to approximate the growth of a population that is as fast as bacteria. There is another way to derive the exponential growth formula. We can use differential equations. Do you remember P of 1 minus P of 0 equals R times P of 0? So we can use change. The change in the population with respect to the change in time is equal to the growth rate and the current population size. If we let the changes to be very, very small, we can replace the delta with derivatives. And from calculus, we know that using separation by variable, we can arrive at the exponential growth formula that we have derived before. Let us extend this model to have a carrying capacity, denoted by K. Using the idea of Verholtz, we can multiply Rp with 1 minus P over K. This is because if the population size is smaller than the carrying capacity, the population can still grow. But if the population size is larger than the carrying capacity, then there will be a decline until it reaches the equilibrium level. Okay, what if we also add constant harvesting? Here, represented by H. To analyze this, let us decompose the right-hand side of the differential equation into two parts. The growth curve, Rp times 1 minus P over K, which is quadratic and can be represented by a parabola. The other one is the harvesting H, which is just a line. We can graph the two curves as this: the growth curve with color green and the harvesting line with color red. If we look just at the growth curve, the equilibria are K, the carrying capacity level, and 0, which is trivial. The maximum growth can reach K over 2. If we consider the harvesting line, the intersection of the green and red curves are the new equilibria. Looking at the rightmost side of the figure, if the red line is above the green curve, then the population will decline. This is because the harvesting rate is bigger than the production in the community. If green curve is above the red line, then there will be growth. But as you see, at the part near 0, it is possible that the population will decline up to 0. So there are two equilibria: the stable equilibrium, which is more desirable, and the other equilibrium, which is unstable. The unstable equilibrium shows risk or danger of extinction. So, you see, by using mathematics, we can have useful insights that can be helpful for decision makers and policy makers. I hope with this brief lecture, I am able to initiate your interest in mathematical biology. Till next time.